So here in this particular video, I have a few rotational kinematics multiple choice questions for you to practice. So the first one is this one. You're given the angular position of 8 plus 3t plus 5t square, and it wants you to identify which statement is correct. Okay. All right. So let's go ahead and do it. I'm just going to go ahead and bust out my angular displacement kinematics function here, which is change in theta equals omega it plus 1/2 alpha t square. Now, why am I doing that? Because the function given in the statement really mirrors theta f, right? Theta of t is the final angular position. So I'm going to go ahead and utilize this. However, you notice in the function that I have here, it says change in theta, but really you're given theta f. So I'm going to go ahead and expand my change in theta so I can get theta f. So change in theta is simply theta f minus theta I, which is equal to the right side of the function, which hasn't changed. And then I'm going to isolate for theta f because the function given is theta f. So here you have minus theta I. So I'm going to go ahead and add theta I to both sides. So it's going to look like this. Okay. So really essentially here I have theta of t, which is equal to theta I plus omega it plus 1/2 t squared. Now this is useful because then I can just use the function given to me and I can just line things up, okay, based on the the time term. So here, theta doesn't have a t. So if you look at the function given, 8 doesn't have a t either, so I'm gonna line that up. Omega t here, once again has a t, but it's by itself. And then there's the 3t term in the given statement in the original problem, right? So I'm just going to line things up based on the t term, right? This has no t, this has a t, and then this has a t square. So just make sure things line up, and I think you can crack these types of problems out pretty straightforward. All right, so let's go ahead and read choice A. Yeah, choice A here says the initial angular position is positive 8 rads. Well, theta I here is indeed 8, and that's a positive value. So I'm going to go ahead and highlight A. Let's go to B. B says the initial angular velocity is 0. Well, that's not true because if you line things up based on the time term, omega I here is 3. Well, it's not 0. So therefore B is false, right? C says the angular acceleration is constant. Well, there's a couple different ways to look at this, right? When the time function in your angular position is to the second power, then right away taking the second derivative yields a constant if you want to do a calculus way. Or if you want to look at this right here, 1/2 times what number, right? Alpha represents that whatever that number is, will give you 5. Well, 1/2 times 10 gives you 5. Well, alpha would then be 10, and 10 is a constant. So therefore C is true. Okay, so I think that's the easier way to look at it without doing calculus stuff. D. D says the angular acceleration alpha is positive 5 rads per second squared. Well, that's not true. 1/2 times 10 gives you 5, implies that alpha is 10, not 5. So this 5 here is kind of a trap laid out for kids if you don't understand that there's a 1/2 in front of alpha, right? So 1/2 times 10 gives you 5, which means alpha is 10, not 5. So I'm going to go ahead and cross D out. So don't get trolled. E says the angular displacement increases at a constant rate. Well, this is false because the function tells you alpha is 10 rads per second squared. Anytime an object accelerates, its velocity is increasing. Therefore, its angular position is also increasing, but it's not at a constant rate. Okay, so I'm going to go ahead and cross that out. E would only be right if acceleration is 0. Like if the object is rotating on a constant rate. Well, if it's rotating at a constant rate, then it's not accelerating. So you have to differentiate between when alpha is 0 versus when alpha is not 0. Okay, so E is crossed out because there is an acceleration, which implies that your angular displacement is not increasing at a constant rate. It's increasing exponentially. All right, let's move on to the next one. So here on the next one, if you need to pause read, you have a propeller, and the diagram here is given. There's a point X in the center of one of the propeller, and there's point Y on the outer edge of one of the propeller. So X is a distance d away from the axis of rotation, or the center of the propeller here, and then Y is a distance to 2d. All right, so it wants us to find the ratio of omega x over omega y, right? What is the ratio between the angular velocity of these 2 points? Well, Here, I'm just gonna go ahead and give you another visual. Here's another propeller, assuming it rotates, what is this, counterclockwise? So this blade here will move there. So I can identify this, right? As point X rotates, it traces out this arc length. As point Y rotates, it also traces out this arc length, okay? However, in both of these movement, the change in theta must remain the same because it's one blade. So as it rotates, regardless of which point you pick on the blade, it has to rotate the same amount of angle, okay? It'd be weird if they rotate at a different angle, because then now the blade is morphed or something like that. It's super weird, okay? Now, why is this particular information useful, right? Point X covers a certain amount of angular displacement. Point Y will cover the same angular displacement because it's one shape. That's because then I can go back to the average angular velocity function. Well, average angular function tells you that the change in angular displacement divided by the time that it rotates will give you the average. But if you notice here, point X and point Y have the same delta theta. It also has the same delta t, or just t here, time of movement. Well, if change in theta is the same and t is the same, that would imply omega is the same, okay? So that's one way to look at it, which means omega x and omega y is the same, so that cancels out. I'll give you a ratio of 1. The other way to look at it, if you like, is to use your average acceleration equation. From hopefully your 1D kinematics day, the final velocity is simply the acceleration times time plus the initial velocity. Okay, but here it starts from rest, so omega I is just 0. So here we have an expression for omega, which is just alpha times t. Well, now I can apply it twice, right? The expression once again asked of us in this first part is omega x over omega y. So I'm just going to go ahead and write that, omega x over omega y. Well, what is omega x? It's just alpha. Well, it's one shape, so it has to have the same acceleration. It's also the same time because it's one shape. Likewise, on the bottom, omega y is just alpha times t. So as you can see, you have two of the same variables on top and bottom, so that would just cancel out. That would just give you a ratio of 1. Or you should just know that regardless of which point on a shape, as it rotates, the one thing that it does have in common is the angular velocity, okay? All right. Let's move on to the second part of this question. Here it says after t, what is the ratio of the linear velocity of x to y? Okay, so to do this particular one, you just have to utilize the linear velocity and angular velocity relationship. Here we have v is equal to r times omega. All right, so I'm just going to apply this function twice. Vx over vy, because the question asks for vx over vy. Right? Well, what is vx? Vx is just r omega, right? But what is r for Vx? R is just d, because if you look at point x is just the distance d away. Well, what's omega? It's just omega x. And likewise for Vy on the bottom. Well, how far is it from the axis of rotation? And once again, in the diagram, here's the center of the whole entire propeller. If you go from the center red dot to where point y is, that is the distance to 2d. That's why there's the 2d on the bottom. And here's omega y. But if you understood the first part of this particular problem, omega x over omega y will always yield 1 because omega stays the same for every point on the propeller. So that will cancel out, okay? So d also cancels out, and that will just give you a ratio of 1/2. All right, so I'm just going to go ahead and cross the stuff out. Omegas cancel out because they're the same, and then just 1/2. So it matches choice D. All right, let's go on to the last one. So here, if you need to pause read, essentially you have a, what is this, a wheel that's initially spinning in the clockwise direction, and then it's gonna come to a stop, okay, after spinning 10 full spins. All right. So the question is looking for how long did it take for it to come to a stop, aka time. So I'm just gonna go ahead and remind you to read carefully. Here it says 10 spins or 10 full spins. Keep in mind that one full spin is 1 revolution, and 1 revolution is equivalent to 2 pi rad. It's important that you convert to rad because angular displacement is in units of rad. Okay. All right. Other than that, if 1 full spin is 2 pi rad, well, 10 full spin then would just be 20 pi, right? So for every, here I did the conversion for you if you really need to see it, but there's 10 full spin, but for every 1 full spin is equivalent to 2 pi rad. So 10 times 2 pi is 20 pi, and the bottom is just 1, so that disappears, and the spin unit here cancels out. Okay. All right. So to do this one, I think the quickest and easiest way is just to use your average angular velocity. So angular velocity can be displacement over time, or it can be final angular velocity plus initial angular velocity divided by 2. It says here it comes to a rest, so I'm just going to go ahead and cross out. Oh, by the way, I totally forgot. I'd like to remind you, you can only use this function if alpha is constant, right? If A is constant. Well, I know A is constant for this one because it says a braking force or a constant braking force. If your force is constant, then your A is also constant. If your A is constant, I can use this particular average function and set them equal to each other. All right. Other than that, omega F here is 0. I'm solving for T. T is on the bottom here, so I like to do this manipulation. I just like to move T up to the top by flipping the function upside down on its head on both sides. So T on the bottom got flipped to the top. Delta, the theta here from the top got moved to the bottom. 2 flipped to the top. Omega I to the bottom. And then T is not by itself yet. So to get T by itself, multiply both sides by change in theta. So this is what it looks like. And really from here, it's just plug and chug, you know. Change in theta here is negative 20 rad because, or 20 pi rad, excuse me. That's because we take the clockwise direction to be negative. Okay, an angular displacement here is a vector, so you do need to put the direction of rotation. All right. Other than that, omega I here is negative 12. Even though the diagram says positive, or it didn't give you a negative symbol or a sign, but you have to pay attention to how things are drawn. This is going clockwise, so it's rotating in the negative direction, so there's why there's a negative sign. Negative and negative cancels out, and times is scalar, so you'd be getting a positive value anyways. So if you do this correctly on your calculator, you should get about 10.47, which is closest to 10.5, so I'm just going to highlight that. Now, if you didn't want to take this approach and you want to, you can totally set up your average acceleration equation equal to change in velocity over change in time. I see it for change in time by doing, algebra, move the delta t up to the top left, move acceleration down to the bottom right. And then from here, you can break up, changing of omega into omega f minus omega I, and then that acceleration on the bottom just gets carried over. However, the problem says omega f is 0, so you can cross that out. So if you want to, you can just plug and chug, right? The negative sign for the operation gets carried down. Omega itself is negative because it's rotating in the clockwise direction. But I highlighted here angular acceleration because you can't really finish it yet, right? Because you don't have the angular acceleration. However, if you want to do it this way, you can. You can use common form for rotation kinematics. Omega f minus omega I equals 2a, change in theta. Omega f is 0, cross that out. So really, if you think about it, omega I is given, right? Change in theta, it was converted to 20 pi rad. So the only thing you don't know is your angular acceleration. And if you find that correctly by doing basic algebra here and plug and chug, plug it back into this alpha, and then complete the calculator work, you should get the same time. Okay, I will leave that for you to practice if you need to. I just prefer the left method just because I can just get it done in one step without having to solve for more stuff. Okay, all right, I hope that helps. Stay nerdy, don't be whack.